Somebody made a puzzle for me, and it's a Funciton program! If you're new to the channel, Funciton is an esoteric programming language that I invented some time ago, and I made an entire video series about it, link to the playlist in the description. But this December I had the absolute honor of receiving a Christmas gift in the form of a puzzle, which is in the form of a Funciton program. It is titled Won't You Take Me To, which is of course a reference to the song Funciton, which sounds a bit like Funciton, I guess. For context, I received this in a Secret Santa style event, but instead of sending each other material gifts, we make puzzles for each other. This particular puzzle was made for me by Jonah Ostrov, and he's done a lot of other puzzle related things, so I warmly recommend that you take a look at the website, link in the description. Alright, let's see if we can figure out what this program actually does. So the obvious thing to start with is to just run it. But if I try to do that, it will just never output anything. It never finishes. Now, when I first received the puzzle, I thought, well, maybe there is a bug in it. But nah, I'll tell you now, it's not a bug. It is fully intentional. The program just takes ages. So we need to be a bit clever about it to see what it would output if it ever did finish. Let's take a look at some of the individual functions in this program and see what they do. I'm gonna start with this function up here, which is called capital B. So the first thing I notice is that it uses the cross junction, which is the one that calculates either shift left or less than, or maybe both, but in this case it's only one of them because the other one is silenced. So let's figure out which one it is. Well, in counterclockwise order, it's always first input, then second input, and then shift left, and then less than. So the one that's silenced is the less than, so the one that's calculated is the shift left. So this piece of code will calculate 4, shift left 4, which is of course 64. So we could replace this with a 64, and the function would do the same thing. And now the rest of the function is totally straightforward. It literally just adds 64 to whatever input it receives. So this is a relatively simple function. So as we progress through the program, we can replace every occurrence of b with plus 64. And that way we can successively simplify the program and eventually deduce what it would actually output. Now I want to show you 3 more examples of interesting functions in this. One of them is the function called age, which I found interesting because at first sight you can see that it uses this function call, which is the push function. It adds an element to the end of a list. I didn't expect this program to use list functions. So to figure out what this function does, let's take a look at this bit here, which is entirely numerical. You can see that there is a bitwise NAND right here, but then there is a bitwise NOT right after it, so it's the same as bitwise AND. And if we AND the 4 and the 2, what do we get? Well, we get 0. So the first thing that goes into our list processing function is the number 0, which we use to represent an empty list. So that's what that is. And then the next thing that happens is that we add the number 4. So now we have a list containing the number 4. After that, we call the same function again with a 3, so now we have a 3, and then we do the same thing with a 2, and then again with a 3, and then again here with a 2, and then finally we have this one here, which adds one last element. And the value of that element is calculated over here, so we need to go through this. Well, this part here is a 4 and a 3, and we're bitwise NANDing them. Well, a bitwise AND of 4 and 3, because they don't have any bits in common, would be 0, so the NAND of it is -1. And then we're NANDing the result of that again with the number 3. Now, -1 NAND anything will always give you the bitwise negation of something, so we get the bitwise negation of 3, which is -4. So by the time we get to this line over here, we now have a list containing 4, 3, 2, 3, 2, and -4. And that list gets passed into this function. What does that function do? Well, if we look at the Funciton library, we find this function here, which says list element. So it's going to return the nth element of a list. And hey, we did pass in a list, didn't we? And the other value that we pass into this function is the parameter to age. So all the function age does is just index into this list. So if you pass in a 0, you get back the 4. If you pass in the 1, you get the 3, etc. Another function that I want to show you is the O function, which doesn't look very extensive, but it uses 2 other functions from the Funciton library that you may not have seen before. So let's find out what these do. So the first one is this one here, the toMusicalNotes function. And as you can see, it says it returns a sequence, by which it means a lazy sequence, of n consecutive integers starting at x. So we're giving it a value, let's say 5, and another value, let's say 4, and it'll give you 4 integers starting at 5. So it'll give you 5, 6, 7, and 8. And then the other function is this one here. And looking at the library is right here. As some of you might have already guessed from the name of this function, it calculates the product of a sequence of integers. Now to abbreviate this, I'm going to tell you that the O function is actually called only once in the entire puzzle. And this one time that it is called, we pass in the number 3 to it. So the number 3 comes in here and it gets passed into the double musical notes function, which means that we end up with a sequence that starts at 4 and has 3 elements. So we get the sequence 4, 5, 6. And then that sequence gets passed into the product function, so we end up calculating 4 times 5 times 6. So the result of this is 120. Okay, those functions were interesting to figure out, but the interpreter can just run these functions. I mean, it can calculate 4 times 5 times 6 just fine. So which part of the program is actually giving the interpreter a hard time? Well, it turns out it's this one here. It's the function j. So I'm going to walk you through this function and you'll see how cleverly constructed it is to make it possible for a human to figure out, but for the interpreter to take years. Okay, we're going to start down here in the bottom. We have another one of those cross junctions. So let's take a look at this. We have one input and then the other input, and then counterclockwise from that we have shift left. So what this will calculate is 3 shift left 3. Now this one we can calculate. 3 shift left 3 is just 24. Now we get to another cross junction, and this time neither of the two outputs are silenced. So we're actually calculating both the shift left and the less than. Now again, in counterclockwise order, since these are the two inputs, the next one is going to be the shift left, which means that this wire here contains 2 shift left 24, which is a pretty large number. So I'm not going to write it out. I'm just going to write 2 shift left 24. Now the other arm of the cross junction is going to calculate a less than, and well, we can just do that in our head. We know that 2 is in fact less than 24, so this will return true, which we represent as -1. Now the next cross junction only calculates the less than, so again we can do this in our head. 2 is not in fact less than -1, so that will return false, which we represent as 0, and then we're going to be adding the 0 onto something, so I can literally just get rid of the plus right there. Then we have another very simple 2 divided by 2, which is of course 1. And here on the bottom we have another shift left. This time we're taking this number 2 shift left 24, and we're shifting it left by 2. So that's the same as 2 shift left 26. But now comes the real doozy. Take a very close look at the order of operations here. We're not shifting left by 1. No, we're taking the 1 and we're shifting it left by this humongous amount. So we end up with a number that has hundreds of millions of bits. That number is going to be absolutely humongous. And I'm just going to write the formula for it right here. Now on the right hand side we have a few more shift lefts, which are a little bit less wild. Here we have a 2 shift left 2, which is of course 8. And then we're taking that 8 shift left 2, which gives us 32. And finally we have 3 shift left 32. Which again is going to be a relatively large number, so I'm just going to represent it as the formula. And now we multiply those two functions and we're left with this. Okay, so we already know that the number that comes out of this is absurdly large. So what does the program do with this absurdly large number? It tries to turn it into a string. Now of course that is perfectly valid Funciton code, but the interpreter is just going to take years to do this, because it's just going to go modulo 10 divide by 10, modulo 10 divide by 10, modulo 10, and it's going to keep doing that until it reaches 0, which is going to take millions upon millions of steps. But we can be a bit more clever about it. We can look ahead and see what the next function after that does. It turns out it calculates the length of that string, so what we're actually asking for is not so much the number itself, but the number of digits in it, when represented in decimal. Now there's a formula that we can use to calculate the number of digits in a number. It's the logarithm to base 10, then floor, also known as round down, in other words, remove the decimal part, and then add 1. You can easily convince yourself that this works. Let's just put in 10, and we find that the logarithm to base 10 of 10 is of course 1, because 10 to the 1 is 10. And the log to base 10 of 100 is going to be 2, because 10 to the 2 is 100. Which means anything between 10 and 100 is going to give us 1 point something something something, which we round down to 1. And then when we add 1 at the end, we get 2 for any 2-digit number. And the same works for all other numbers. Now we need the number of digits of this humongous number. let's remind ourselves what shift left can be expressed as. Remember that x shift left y is actually the same as x times 2 to the power of y. So I'm going to replace all of the shift lefts here with times 2 to the power of. Of course, we can just get rid of the 1 times, that does nothing. And 2 times 2 to the power of 26 is of course the same as 2 to the power of 27. Now let me move the 3 times to the end, and then we can do another simplification, because we've got 2 to the power of something times 2 to the power of something else. We can put that together into a single 2 to the power of, and then just add the exponents. Okay, we've simplified this quite a lot. Now let's apply the formula for the number of digits, which is log to base 10, floor, and then plus 1. Next, let's apply the formula that says that if you multiply inside of a logarithm, you can just add the individual logarithms. And now, in order to be able to simplify this monstrosity over here, we're going to need to change the bases of the logarithm. We want the logarithm to base 10, but in order to cancel it with the exponentiation with 2, we need the log to base 2. Well, fortunately, there is a formula for that as well. The log to any base is actually the same as the log to some other base divided by the log to the new base of the previous base. Which means we can just change the log to base 10 to a log to base 2 as long as we divide by log to base 2 of 10. And now finally we can cancel the log to base 2 with the 2 to the power of. And finally, we're left with a formula that is much more reasonable to calculate. So now I can just write out that formula on the command line and just get the answer. You can see that the number is over 40 million, which means that in order to calculate that number, the Funciton interpreter would first have had to do divided by 10 and modulo 10 40 million times just to construct a huge string, and then it would have to count up to 40 million one at a time in order to calculate the length of that string. So coming back to the program, we now know that this part of the function calculates the number 40,403,573. Okay, so that's the first hurdle that the puzzle presents us with. So now that we can figure out what the program does, what does it actually output? Well, it turns out it outputs this string. Now, if you're not super familiar with puzzles, you might be forgiven if you don't know what hashi is. Well, it's actually short for hashi wo kakeru, which is a type of logic puzzle. And here's an example of that puzzle. On the left, you see what the solver is given. It's literally just some numbers in circles. And the aim of the game is to connect these numbers with lines or double lines in such a way that every number tells you exactly the number of lines that come out of that circle. None of the lines cross each other, and the whole thing is a single connected thing, so you can't have multiple isolated pieces. Okay, but what does that mean in the context of our puzzle? All we just did is we just ran some Funciton code and we got back the word hashi. What do I do with that? Where's the hashi puzzle? Well, if we look through the Funciton program, and in particular we look at all of the literals, we'll notice that they're all relatively small numbers, like 2, 3, 4, and 5. So why don't we take every character in the source code that is not a digit or a new line and replace it with a space? And then we find that we get a sea of numbers, which actually looks very much like a valid hashi wo kakeru puzzle. So I've transferred all of these numbers into a hashi wo kakeru website, and now we can start solving this hashi wo kakeru. What I noticed straight away is that this 4 up here only has 2 directions it can go to, and since any direction can only be 2 bridges at most, it means that we must have all of those bridges in those directions. The same applies to this 4 over here. And it also applies to this 4 because there is no number that is directly below it. You'll notice that it's not aligned with any of the other numbers here. Once we've done that, we'll notice that there is a 5 here which already has 4 bridges, so it needs just 1 more, and there's only 1 direction it can go to, which is down. And we can do the same thing here and here. There is also a lonely 1 right here at the bottom that has only 1 direction to go to, so we can put that in as well. Now let's take a look at this 5 down here. Well, it turns out there isn't any number directly above it, so the only other direction it can go in is to the left, so we can just fill in the remaining 2 bridges there, and then the 3 can only go up. Now here's another really cool deduction. Let's take a look at this too. Imagine that both of its bridges were to go to the right. Well, it would connect to another 2, which means that this connection between the 2's is now entirely isolated from the rest of the puzzle. Neither of those 2 circles can have any more bridges coming out. So we can't actually have a double bridge to the right, but for the same reason we also can't have a double bridge going up. Which means that both of these directions can have only at most 1 bridge, but we need 2 bridges, so both of those directions must be a single bridge. And we can say the same thing about this 2 here, because there is no other number above it or to the left, so we can only go to the right. We can also do the same thing here. This 2 cannot have 2 bridges going up, and it can also not have 2 bridges going left. So it must have 1 bridge in each of the 2 directions. And then this 2 can only go left. And then the same thing applies to this 2 up here in the corner. Now this 2 can only go left, this 2 can only go down. Now let's take a look at this 3 over here. Now that 3 already has a bridge, which means that it needs 2 more. But they can't both go up, because once again, this entire region would now be isolated from the rest of the puzzle. And they also can't both go to the right for the exact same reason. So we must have exactly 1 in each of those directions. And now that 2 can only go in 1 direction, and this 2 has no digit above it or to the right, so it can only go down. And then this 3 only has 1 direction left. This 2 has only 1 direction left, and this 2 down here also has only 1 direction left, I could have noticed that sooner, which forces that 3 to go to the right. This 2 over here can only go in 1 direction. This 3 already has 2 bridges, and the remaining bridge can only go in 1 direction, which forces that 3 to go up. Here's another 2 that can't have both of its lines go down, and it can't have both of its lines go left, and there are no other directions to go in, so it must be 1 of each, which forces this 2 to continue in this direction. This 2 doesn't have anything above it, so it can't go up, it can only go down, and then this 3 can only go here, which forces the last bridge for the 4 to go up. Just as before, this 2 is also in a corner, it can't have 2 bridges up and left, so it must be 1 of each. That means this 2 can only go left now. This 2 doesn't have anything below or to the left, so it can only go up. And this 2 over here can only go up, and that forces the 3 to go left. This 2 can only go left, this 2 can only go up. And here's another 2 that can't go left or down, and if it had a double line it would be isolated from the rest of the puzzle, so again it must be 1 line in each direction. Now this 2 can only go up, this 2 can only go right. This 2 over here has something similar going on. It can't have 2 lines going to the left because that would isolate it, so it has to have at least 1 going down. But we don't know if it's 2 going down or 1 down and 1 left, at least not yet. But we can say the same thing about this 2. It can't have both bridges going right, so one of them must go up. And the same is true of this one here. It has a 2 to the left, which means that at least 1 bridge needs to go up. And of course this 2 also can't have both bridges going to the right, so there must be at least 1 going down. Now let's see what happens if this were a double bridge. That would actually satisfy the 3, so it can't connect to the left. And then this 2 can only go to the right, which satisfies the 2. And also this 2 can only go down, because the left is already satisfied. And that would satisfy the 3. So now we have an isolated island over here, which is not allowed, so we can undo that, and we now know that this line cannot be double, so the only other place for the 2 to go is to the right. And of course the argument works the other way. If this were a double line, then this 2 would now be forced to have a double line going up, and then once again this entire island is isolated, so we can undo that, and we know that this is not a double line, so the 2 can only go to the right. And that forces both of these 3s to branch out. This 3 only has 1 direction to go, and then that, and then that, and then that. And this 3 has only 1 direction to go, and then the 2, and then the 3. Now in a similar vein, we can say the same thing about this 2 here. If that had 2 lines going down, it would then force this 3 to have 2 lines going up. And now the 4 only has the up direction to go. And now everything down here would be connected, but there would be an island left over up here in the top right. So we can't have that. So this line cannot be a double line. It can only be at most a single line, which means that at least one of the 2 bridges has to go left. And if both of them were to go left, well then something very similar happens. We would have to connect this over here, and then the only place for the 3 to go would be over here to the right, and the 2 would have to connect with the double line to the right. And now once again this piece of island here is isolated. So this is not a double line either. So we need 1 line going to the left and 1 line going down, which forces this 3 to branch out, this 3 to branch out, this 4 has only 1 direction to go, the 3 has only 1 direction to go, and all the rest just falls into place. Now I'm sure while I was going through this you already noticed what happened here. We're getting another Funciton program! That's right, the author designed that first Funciton program in such a way that it would contain another Funciton program in the form of a Hashiwo-Kakero puzzle. How amazing is that? But there's one minor snag, because the solution to the Hashiwo-Kakero puzzle only tells us all of the lines. But of course we have something like a literal box up here, and another one down here, and another one on the right. Now, these could theoretically be empty and they would be standard input, but then we wouldn't know what to pass into the standard input. But on top of that, we have something down here. It's a bit squished, but it's a function call. It has 2 double lines and 2 single lines. So we need to figure out what function to call. How do we do that? Well, in order to figure this out, let's take a look at the original puzzle, and let's look at where each of these individual numbers that make up these boxes are. In particular, let's take a look at this top left one, which consists of 2 4s on the top and then a 4 5 4 on the bottom. Going back to the puzzle, we find that these 4s and the 5 are right here. And you'll notice there is something right smack dab in the center of that. The same is the case over here where we had another literal box, and once again there is a single box that's right in the center of that. And as for the function call right here at the bottom, we can see that that is created by these boxes, and in the center of that we have the increment function, the musical sharp symbol. So what do we do? Well, there's really only one thing we can do. For the literal boxes, we have to put a number in them, but we're given a character like a capital G. Well, Funciton is all about Unicode, so why don't we replace that with the Unicode code value? So what we end up with is this. That's right, it's another Funciton program, which we can just run. And, well, it'll output something, but unfortunately the Windows console is a bit limited and doesn't quite show it. So I'm going to pipe this into a file, and then I'm going to open that file in Notepad, and this is what we get. A nice little present. So now we're done with the first part, which says hashi. What do these numbers in parentheses mean? Now, if you've ever done hunt puzzles before, you'll know that this is a so-called enumeration. It tells us how many words are in the solution and how many letters each word has. So we're looking for a 2-word phrase, where the first word is 4 letters, and the other one is 3. And on top of that, the answer needs to be the answer to this question. What sort of present did I make you? So our 2 clues are, we have an emoji that looks like a present, and we have the numbers 4, 3. How do we describe that emoji using such words? The answer is, of course, gift box. Which makes perfect sense because the puzzle I received was a gift, and it's a Funciton program made of boxes. It's literally a gift box. Well, this was an absolutely amazing puzzle, and it was exactly the right thing for me, covering exactly my interests. Puzzles and esoteric programming languages, especially my own. It was such an incredible honor to see my own esoteric programming language represented in a puzzle that was a gift for me. Thank you so much to Jonah Ostrov for creating this puzzle for me. And again, take a look at his website. He has made a lot of cool other puzzles, link in the description. And I'll see you in the next video.